Okay, good morning. So we are going to discuss second part of thermodynamics, that is different thermodynamic process. Different thermodynamic process. Pressure, volume, temperature, absolute temperature are thermodynamic variables. Pressure, volume, temperature, thermodynamic variables. In the thermodynamics, we have different thermodynamic process. So there are mainly four processes are there. One is isothermal process. Second one, adiabatic process. Third one, isobaric process. Fourth one, isochoric process. So these are the four thermodynamic processes: isothermal, adiabatic, isobaric, and isochoric. Okay, and gases having two type of specific heats: specific heat at a constant pressure and specific heat at a constant volume. And these two topics we have to discuss in this video. First of all, what is the isothermal process? The change in volume and pressure without change in temperature is called isothermal process. Volume and pressure can change, but temperature cannot change. That is called isothermal process. So in isothermal process, temperature constant. That means internal energy constant. That means change in internal energy zero. U constant, du zero. Change in internal energy zero. And it is the slow process. Heat transfer from high temperature, heat transfers from system to surroundings to system. Heat exchange between system and the surroundings, heat can exchange. And the next, it is the slow process. The walls of the vessel are made with good conducting material. Because heat can exchange between system and the surroundings. Walls are good conducting materials. And in this process, PV is a constant. Boyle's law, PV is equal to constant holds good. PV constant holds good. And in this process, work done, how much? Work done is equal to 2.303 nRT log V2 by V1. This is the work done in an isothermal process. Work done in an isothermal process is this one. Okay. And the PV graph constant slope, PV graph if you plot, we get a graph inversely proportional. So this is called isothermal curve. Okay. Next about the adiabatic process. The change in volume and pressure in a thermally isolated system. That means the heat cannot exchange between system and surroundings. Heat will not go outside or cannot enter into the system. That is called adiabatic process. Volume and pressure can change. And that means the temperature is variable. But volume and pressure can change, temperature also can change. And the temperature variable means internal energy can change. Internal energy can change. So du is not a constant. Du is a variable. You may increase or decrease also. But heat transfer is zero. Heat cannot exchange between system and surroundings. dq 0. And fourth point. So heat is not exchanged means walls are made with bad conducting materials. Walls are bad conducting materials. Fifth point. Walls are made with bad conducting materials. Fifth point. Points does not hold good, but PV power gamma is equal to constant holds good. PV power gamma constant. Sixth one, work done in the adiabatic process. The formula is 1 by gamma minus 1, P1 V1 minus P2 V2. And one more formula is there, R by gamma minus 1 into P1 minus P2. This is also work done formula. And if you plot the graph, pressure volume graph, we can get like this. So adiabatic curve is this one. The slope of adiabatic curve is gamma times the slope of isothermal curve. The slope of adiabatic curve is gamma times the slope of adiabatic curve. Okay. And in the adiabatic process, PV power gamma constant. What are the relations between PV and T? Adiabatic relations, very important. Adiabatic relations. One is PV power gamma constant. Second one PV power gamma minus 1 constant. Third one P power 1 minus gamma by gamma constant. These are adiabatic relations. And gamma values you have to remember. Monatomic gamma is equal to monatomic gamma 5 by 3. Diatomic gamma is equal to 7 by 5. Polyatomic gamma is equal to 4 by 3. 8 by 6 or 4 by 3. So this is about adiabatic process, isothermal process and adiabatic process. Next, isobaric process, and PV is equal to constant. Then you can write dP P into dV plus V into dP is equal to 0. Differentiated, partial differentiation. Therefore, dP by P is equal to minus dV by V. Isothermal process dP by P is equal to how much? dV minus dV by V. Adiabatic like the PV power gamma constant and differentiating both sides and simplifying, we get delta P by P is equal to minus gamma times delta V by V. And isothermal bulk modulus represented by K. K isothermal is equal to pressure P. K adiabatic is equal to gamma P. K adiabatic is gamma times of the P, gamma P. Isothermal bulk modulus is P, adiabatic bulk modulus gamma P. And slope of adiabatic curve is gamma times the slope of isothermal curve. Okay. Next, isobaric process. Isobaric process means change in volume at a constant pressure. Change in volume and temperature at a constant pressure is called isobaric process. In this process, pressure constant. And first of thermodynamics, dQ is equal to du plus dW. Nothing is zero. In isothermal process, du zero na. Therefore, dQ is equal to dW. Isothermal process. In adiabatic process, dC is zero na. 0 is equal to du plus dW. This is adiabatic process. First of thermodynamics become like this. But here nothing is zero. So isobaric process, dQ is equal to du plus dW. And work done is equal to PdV. Isobaric process में work done is equal to dilated to change in volume. And next one more process is isochoric process. Isochoric process. Here volume remains constant. Volume remains constant. So work done 0. Work done dW is equal to PdV is equal to 0. Volume constant. Therefore first law of thermodynamics become dQ is equal to du. This is the first law of thermodynamics. So these are the 4 important different thermodynamic process. And then one more. This is isochoric process graph. This is isothermal, isochoric, and this is adiabatic, and this one isochoric. This isobaric. Okay. Now work done in isothermal process W1, adiabatic process W2, isobaric process W3, isochoric process W4. Arrange them in an increasing order. So, or decreasing order. So, maximum work done is isobaric because area covered with the volume axis is work done. So, more area coming for isobaric. W3 greater than. Next, isothermal process W1 greater than adiabatic process W2 greater than last one isochoric process W4. This problem is a very important model. So work done maximum in isobaric process, minimum in isochoric process. Work done 0 isochoric process, work done is 0. Next, we have one more topic, that is specific heats of gas. Actually, solids having only one specific heat, but gases having 2 specific heats. One is at a constant pressure, second one at a constant volume. So this one is 1 by n dq by d theta, and this is 1 by n du by d theta. At a constant pressure, the heat supplied is utilized to increase its internal energy and to do the external work. And but at constant volume, whatever the heat supplied should increase the internal energy only, no external work. That's why Cp greater than Cv. Cp greater than Cv. The heat supplied at constant pressure utilized to increase the internal energy and to do the external work. So more heat is required. So that is Cp. At a constant volume, heat supplied utilized to increase its internal energy only. So Cv is less. So Cp greater than Cv. Therefore, Cp minus Cv is equal to capital R. Universal gas constant. Capital R. Capital value we know 8.314 joule per Kelvin per mole. Joule per Kelvin per mole. And Cp, Cv also 2 types. These are called molar specific heats. Molar specific heats. Next we have gram specific heats. Gram specific heats. 1 by m dq by d theta. Cv 1 by m du by d theta. And these are called gram specific heats. Therefore here Cp minus Cv is equal to small r. This is gas constant. Gas constant value depends on the gas and the units joule per Kelvin per kg per Kelvin. Joule per kg per Kelvin or Kelvin per kg. Joule per Kelvin per kg. Here mole, here kg. That is the difference. And the capital R is same for all gases and small r is different for different gases. So this is about these are about specific heat of gases. Okay. Now some heat energy is applied to the gas. Some heat energy is applied to the gas. fraction is utilized to increase its internal energy? du by dq, how much? And what fraction utilized to do the work done? dq by du, how much? These are the points. So, first of thermodynamics, we know dq is equal to du plus dw. From that, cross multiply here, we are getting dq is equal to n cv d theta. du is equal to n cv d theta. Okay, and we know first of thermodynamics, substituting these two there and simplifying, we get dw is equal to n r d theta. dw is equal to n r d theta. Work done. pdv or n r d theta. So here one fraction is utilized to increase the internal energy. du by dq how much? n cv d theta by n cp d theta. d theta d theta and then cancel. We get 1 by cp by cv. 1 by cv by cv means gamma. 1 by gamma fraction is utilized. What percentage? What percentage is into 100? So du by dq into 100 is equal to 1 by gamma into 100. What percentage utilized to increase its internal energy? What fraction utilized for work done? So 1 minus 1 by gamma fraction utilized for work done. Percentage means 1 minus 1 by gamma into 100 percentage. So dw by dq into 100 how much? అంటే 1 minus 1 by gamma into 100. 1 minus 1 by gamma into 100. And the two gases are mixed. Two gases are mixed. Then resultant mixture Cp value how much? N1 Cp1 plus N2 Cp2 by N1 plus N2. And resultant Cv is equal to N1 Cv1 plus N2 Cv2 by N1 plus N2. Therefore, gamma is equal to Cp by Cv. We can calculate Cp by Cv. On the tabular form, monoatomic gas, diatomic gas, polyatomic gas. What about Cv value? What about Cv value? What about gamma value? What about the examples? Monoatomic gas, Cv value 5R by 2, Cv value 3R by 2, gamma value 5 by 3, that is 1.66. Example, helium, neon, argon, krypton, etc. Diatomic gas 7R by 2 and 5R by 2, and this is 7 by 5, gamma value 1.4. H2, O2, N2, etc. Diatomic gases. Polyatomic gas means 8R by 2, 6R by 2, 8 by 6, R 4 by 3, that is 1.33, and ozone, carbon dioxide, H2S, etc. These are the examples for polyatomic gas. So gases are three types: monoatomic, diatomic, and polyatomic. Cp minus Cv is equal to R. Cp by Cv is equal to gamma. Then express Cp and Cv in terms of gamma and R. Cv is equal to gamma by gamma minus 1. R by gamma minus 1. How? Cp minus Cv is equal to R. equal to gamma CV. Substitute here gamma minus 1 bracket into CV is equal to R. Therefore, CV is equal to R by gamma minus 1. CP is equal to gamma R by gamma minus 1. CP is equal to gamma R by gamma minus 1. First law of thermodynamics, dU is equal to du plus dW. One table from monoatomic, diatomic, polyatomic. For this, du by dq how much? Du by dq into 100 how much? dw by dq how much? dw by dq into 100 how much? For monoatomic gas, the fraction 1 by gamma. This is 1 by gamma. 1 by 5 by 3 and 3 by 5. Fraction is 3 by 5. Percentage means 3 by 5 into 100. 3 by 5 into 100 means 60%. So this one 1 minus 1 by gamma. And 1 minus 3 by 5, 2 by 5. And 40%. 2 by 5 and 40% monoatomic gas. And for diatomic gas, this is 5 by 7, 5 by 7, because 1 by gamma, 1 by 5 by 3, 1 by 7 by 5, therefore 5 by 7 will come. And percentage is equal to 500 by 7, 71.2%, 71% approximately. And this one 2 by 7, 29%. And for polyatomic gas, this is 3 by 4, and then 75%, and 1 by 4, 25%. This table form an important table form. Okay. And if you know gamma values already represented in the last table, then adiabatic process problems also we can do easily. Adiabatic process, we can do the problems on adiabatic process. And see one more problem. Cp minus Cv is equal to Kepler molar specific heats. Okay, for hydrogen, Cp minus Cv is equal to N. For oxygen, for hydrogen, for oxygen, Cp minus Cv is equal to M. What is the relation between N and M? For hydrogen or oxygen, Cp minus Cv is equal to Kepler. So is equal to capital is equal to capital. So N is equal to M. If Cp minus Cv is equal to small r gram specific heats. These are the gram specific heats. Then they say Cp minus Cv is equal to N for hydrogen. For oxygen, Cp minus Cv is equal to M. What is the relation between M and N? So, Cp minus Cv is equal to small r. Small r is nothing but capital R by molecular weight. This is also small r, capital R by molecular weight. Small r are different. For different gases, gas constant is different. Therefore, N by M is equal to, dividing these two, R are cancelled, M2 by M1. So, oxygen molecular weight 32, hydrogen 2. So, 16. Therefore, N is equal to 16 M. This is the relation between N and M. N is equal to 16 M. m is equal to 16 m. Okay.